Dr. Manan. I'm assistant professor in the Department of Mechatronics Engineering, UT Texla. And today I'm here to present. Okay, before that, this is my qualification. These are my interests, and this is the channel on which I upload my videos. Okay, I'm discussing chapter number 11 of Professor Siciliano. Please forgive my pronunciation. Yeah, its complete name is Bruno Siciliano, and the book title is Robotics Modeling, Planning and Control, published by Springer. I'm discussing its chapter number 11, and today I'll be covering kinematic model. So, particularly this topic. So let's go there. Before I begin any further conversation, let me put that this lecture is a continuity of my previous lecture, which is chapter number, which is lecture number 7, I guess, in the same series. So if you want to follow up, please go through that section before. Okay. Um, Basically, the system of K-Fafin constraints, which is shown in 11.3. So let me go over there. Yeah, there it is. Yeah, this one is the constraint, like A transpose Q multiplied with Q dot is going to be equal to 0, which pretty much roughly means that in a certain direction with a velocity you cannot move. So that's what it is trying to describe. So just like that, you cannot move your bicycle sideways. You cannot obviously move your car sideways, but you definitely can achieve the position and orientation in sideways by going forward and then coming back and something like that. So this is a Fafin constraint 11.3. So let me go back to my slide. Okay, and there we are. So the system of K-Fafin constraints, which are shown 11.3, entails that the admissible generalized velocities at each configuration Q belong to the n minus k dimensional null space of matrix. So denoting by G1 of Q goes down to G of n minus Q, a basis of null space. The admissible trajectories of the mechanical system can be characterized as the solution of nonlinear dynamic systems. So what does it mean? Let me explain that. Okay, it means that if you want to move your robot in a certain direction, that velocity must belong to n minus k null space, dimensional null space of this matrix, which means that it must follow the constraint defined in equation 11.3, which actually means that whatever the velocity is, sideways velocities is going to be equal to 0. Um, denoting by G1 of Q down G minus Q, a basis of null space of A transpose Q, the admissible trajectories of the mechanical system can be characterized as a solution of nonlinear dynamic system, which has vector field Gj to Uj, which is state, which is going to be the input vector, and this is going to be some vector field which is mapping Q to Q dot with the help of input. So that's what it is. Here Q is the state vector and U is the input vector. This system is said to be driftless because one has Q dot equal to 0 if the input is 0. Now let me tell you that these kinds of systems do not exist in practical situation, but considering a mobile robot which is moving quite slow space, with a quite slow speed, these equations can be used. This equation can be used to describe its motion. So it's like as long as the motors are running, the robot is moving, and as the motor stops, motors stop, the robot stops moving. So but in actual we have another factor, which we'll discuss in some other time. For the simplicity, it's going to be driftless if there is no input. Now the choice of input vector fields, g1 of q to gm of q and thus of matrix gq in 11.10 is definitely not unique. Correspondingly, the components of U may have different meanings. In general, it is possible to choose the basis of null space of A transpose of Q in such a way that UJs have a physical interpretation, as will be shown later for some examples of mobile robots. So, yeah, we'll discuss when time is good, when the topic is up for discussion. However, the input vectors U may not be directly related to the actual control inputs that are in general forces and or torques. For this reason, equation 11.10 is referred to as the kinematic model of the constraint mechanical system. So one must be very clear that this U does not mean an actual control input. The holonomy or non-holonomy of constraints 11.3, which was the Pfaffen constraints, can be established by analyzing controllability properties of the associated kinematic model 11.10, which is this one. Okay. In fact, two cases. So for that kinematic model, two cases are possible. So how do we analyze holonomy or non-holonomy of the system? So let's discuss the both of the two cases. Number one, if the system 11.10 is controllable given two arbitrary configurations qi initial state and qf final state in configuration space C, there exists a choice of ut, that is the input vector, that steers the system from qi to qf. Pretty obvious. That is, there exists a trajectory that joins the two configurations and satisfies the kinematic constraints defined in 11.3. Therefore, these do not affect in any way the accessibility of configuration space C, and they are completely non-holonomic. Now, case number two. If system is not controllable, the kinematic constraints reduce the set of accessible configurations in C. Hence, the constraints are partially or completely integrable depending on the dimension of V, which is less than going to be n, of the accessible configuration space. So what is V and what is n? N are definitely the number of independent, n is the number of degree of freedom, and m are the number of inputs. So if number of inputs are going to be greater than the integrable V, which is accessible configuration space, and this space is less than n, the loss of accessibility is not maximal, and thus constraints 11.3 are only partially integrable. The mechanical system is still non-holonomic. So there is a point. The point is, number one is completely non-holonomic, in which we can achieve initial configuration to final configuration by using suitable u of t. However, if it is not controllable, it is somehow partially integrable. So the loss of accessibility is not maximal in this case, and the mechanical system is still non-holonomic. So we'll discuss some of its examples. However, in case B, if V becomes equal to M, it means number of inputs, the loss of accessibility is maximal, and constraints 11.3 are completely integrable, not partially. So the system, mechanical system, is holonomic in that case. So it becomes completely holonomic, which means that you can not achieve those configurations, whatever you whatever it takes, do whatever you want, but you are not able to achieve those configurations. So in particular, controllability may be verified using the accessibility rank condition. So I'm going to discuss what it is. So let's consider this accessibility rank condition. It's a dimension of delta A of Q. It's going to be N, where obviously delta A is the accessibility distribution associated with system 11.10. The involutive closure of distribution delta is equal to span G1 down to Gm. The following case may occur. Number one, if 11.11 holds, system 11.10 is controllable, and the kinematic constraints 11.3 are completely non-holonomic. So I'll discuss what is what is accessibility distribution, how do we calculate, and what it means by involutive closure. So let's begin. Um, I took this helping material um, from the website of Professor Alessandro Di Luca. I'm sorry for my pronunciation. He is an Italian professor, a great professor. His lectures are there in his website, and yeah, it's awesome. So let me let me describe what is basically accessibility rank condition and what is accessibility distribution, what it means by involutive closure of distribution. So I want to describe these two terms, and I'm making the background for that. So first of all, let me describe Lie derivative. How do we define it? It's simply we define it by taking partial differentiation of function f, and we're going to multiply it with x. So for example, I'll explain with an example, but keep this in mind in this position. And then we have Lie bracket, where we have two vector fields, yeah, x and y, and to take that this Lie bracket is defined in this way. So take Lie derivative of y minus with respect to x, and then Lie derivative of x with respect to y. So that's how we're going to calculate. So let me begin with an example. So this is a vector field G1 and G2. So it's described in a matrix G. So it's going to be cos theta, sin theta, 0, 0, 0, and 0. So G1 is this one, and G2 is this one. So how do we take its this one Lie bracket? So we're going to write it down as xy and x and y. So first x1 is down, y is over here, which is G2, and then y is down and x over here. So that's what it is. So now further writing it in this form. So let me write that in this form: partial G2 over partial Q with, and it's going to be multiplied with G1, and then G1 by Q1, and this Q is definitely a state vector. So we have to integrate this whole system with respect to state vector, which is going to be x, y, and theta. So let me write that over here. So Q is going to be equal to x, y, and Um, so if we differentiate this one with respect to x, y, and theta, so first element with respect to x, then with respect to y, then with respect to theta, we'll get this 0, 0, and 0. And then second element with respect to x, with respect to y, and then with respect to theta, we're gonna get 0, 0, 0, and so on. G1, which is this, um, this vector field is going to be as it is, and then we're going to differentiate g1 with respect to state vector. Sorry. So this one is cos theta. So I'm very sorry. So this one is cos theta, and if we differentiate with respect to x, it's going to be 0. If we differentiate with respect to y, it's going to be 0. And if we differentiate with respect to theta, it's going to be minus sine theta. And so with the 0, 0, and cos theta, and again 0. And g2, which is here, is going to be as it is. And we get sine theta minus cos theta and 0. So Lie bracket of this vector field is equal to this one. So let me erase that. Now I want to discuss an example of unicycle robot. Okay, for the system, let's consider x dot is equal to aq plus bu. It is going to be like linear system, and if you consider non-linear system, it's going to be f of q plus g of q into u. The controllability matrix is this one, C. Okay, this is different than configuration space, so I've mixed up variables, but here is like controllability matrix. So we know for linear system it's equal to b, a square b, and so on up to a n minus 1b. So if the system is let's say 4 degree of freedom, it's going to be a3 into b. The n is the rank of matrix A or dimension of f. Now Lie bracket is equal to minus f. G is going to be this one, and it's going to be equal to AB. Now going further, A square B is going to be equal to f comma g bracket and the whole Lie bracket. So where we calculate simple b, it's going to be the G matrix containing both of the vector fields g1 and g2, and for the Lie bracket it's going to be equal to ab, and this is going to be fg, and then for a square b it's going to be double f and then ft. F is just like a, right? So 3a, a3, aqb means f, 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 and then g, and so on. So accessibility distribution is nothing but the same controllability matrix C written as delta of A. So delta of A is going to be equal to C matrix. Considering driftless model of a unicycle robot, which is like this, in where x dot is equal to cos theta into v, which is a linear velocity, and v dot equals to sine theta into v, and theta dot is equal to omega, obviously. So let me call this vector field as g1 and this vector field as g2. So as a whole, we can write this this whole system in this way. So the controllability matrix is going to be equal to accessibility distribution, and we can write it g1, g2, and this one. We can see that rank of or the dimension of this accessibility distribution is equal to 3, which is equal to n. So the system is controllable, and that's the point. Okay, the smooth distribution delta associated with the m smooth vector fields g1 down to gm is basically the map that assigns to each point x, and in our case it was q, which belongs to its n-dimensional space, a linear subspace of its tangent space, like that. That is, delta of x is going to be equal to span g of x to down to g of m, which is going to be subspace of its tangential space. So what it means is basically the smooth distribution is a map that is assigning this x a linear subspace of its tangent space. So but tangent means x dot. So this distribution is mapping, and these are the vectors which span the space. So we put in x, this vector spans, and this becomes a subspace of D of x. This delta is said to be non-singular if dimension of delta of x equals to r, that is constant for all x. It's going to be non-singular. In this case, r is called the dimension of the distribution. Moreover, delta is involutive if it is closed under the Lie bracket operation. So if the Lie bracket belongs to this distribution delta, for all g1 and g2 belongs to this delta. So it means that the Lie brackets also belong to the accessibility distribution, and g1 and j for all others vector fields also belong to accessibility distribution. So they are going to span this space. The involutive closure of delta A bar of distribution A, delta is its closure under the Lie bracket operation. Hence, delta is involutive if and only if delta bar is equal to delta. Otherwise, it's not involutive. I hope you get the point, and if you have any confusion, please write me. I'll explain more. So, more background from the lectures of Professor Alessandro. A non-singular distribution delta on R of an n-dimensional space of dimension k is completely integrable if there exists n minus k independent functions hi such that the Lie bracket of those independent functions is going to be equal to 0. Or otherwise, that is for all x that belongs to n-dimensional space, for all g that belongs to accessibility distribution, and I belongs to 1 down to n minus k. So this delta has a dimension k, it is on n-dimensional space, is integrable if n minus k independent functions uh, exist. Okay. So in this case, each hypersurface defined by the level surface, which is x belongs to n-dimensional space, h1 of x belongs to c1, and h in minus k to cn minus k is called an integral manifold of delta, or accessibility distribution. So equation this 1.4 by Professor Alessandro indicates that accessibility distribution coincides with its tangent space, coincides with the tangent space to its integral manifold at x. So it means that the accessibility distribution delta x um, coincide the integral manifold at x of accessibility distribution um, coincides with the tangent space. Okay, so um, so it pretty much means the same thing which is written, that it indicates that accessibility distribution coincides with the tangent space to its integral manifold at x. So integral manifold and tangent space coincides at x. So controllability, consider a nonlinear control system in the form x dot equals to f of x plus some m inputs with the vector field g is called fine in the inputs uj. The state vector x belongs to some n-dimensional space, and each component of the control input u belongs to m-dimensional space and takes values in the class of piecewise constant function u over time. So it is taking value. It's a piecewise continuous constant piecewise. I think this is a piecewise continuous. And let me denote this by x t to comma 0 x naught u. the unique solution of equation this 7.14 at time t greater than 0 corresponding to a given input function u and the initial condition x0. So unique solution, we are describing it with this something, this variable, or this by these notations. So this is going to be t greater than 0. Initial condition is x naught. Starting time is at, okay, t, this is t some after some time t, and it's going to be equal to 0. It's going to be greater than 0. So the control system 7.14, which is this one, is controllable if for any choice of x1, x2 that belongs to n-dimensional space, there exists a finite time t and an input u, which is 0 to t. Okay, so it's within this 0 to t, that maps to u such that x t on to xt comma 0 comma x1 to u is equal to x2. So it means that if you're taking from the initial condition x1, which is here, at time starting at time 0, you are going to reach at x2 within the duration of time t, and there is a u defined for that. Unfortunately, the general criteria for verifying this natural form of controllability um, does not exist. Sorry for my grammatical mistake. So what do we do is we define a neighborhood. So given a neighborhood v of x naught, let me denote it by some r raised to power v. It's going to be the neighborhood of x0 comma tau, the sets of states psi for which there exists u, which is 0 to tau, which maps to u, such that x tau comma 0 comma x naught comma u equals to psi. So it means that starting from x naught at time 0, after some time t greater than 0 but less than tau, with the u input we are going to reach at psi, and this psi is gonna be is is a state which is in is a state which is definitely um, so these are the states psi, which are definitely part of a set, and these states can be reached within time tau by using some input u, and further. So that's what it means, that we have some states psi we can reach from x0 to psi within some time interval tau to 0, and there is important thing is that this belongs to, and xt at time t from 0 to t and x naught to u is belongs to the neighborhood v of x naught for t less than tau. So it means that we are reaching from state x0 to psi, and during this period we are in the neighborhood of x naught, and definitely the time is going to be lesser than this tau. So before we reach over there, we go through this value, we go through this procedure, and we go in the neighborhood of x naught. In other words, this r x naught comma t, it's going to be obviously v, is the set of states reachable at time tau from x naught with trajectories contained in v, that is the neighborhood of. Also define this rv of t x naught is going to be the union of t less than or equal to tau or v of x naught into comma t. So these are the union and these are defined in this way. So these are the states which can be reached within a time interval tau, and the trajectories contained in this neighborhood P. Okay, this is a set of states reachable within time t from x naught with the trajectories contained in the neighborhood of P. So the control system, which we discussed at 7.14, let me go back and show it. So this one is called locally accessible, okay, locally accessible from x naught if for all the neighborhoods v of x naught and all the t set of reachable states contains a non-empty open set omega. In general, it means that there can be many trajectories from x naught, and at least some of them are reachable. So this will be more clear. This will be clear by an example, which is over here. But let me describe small time local controllability. It is small time local controllable form x naught. System is definitely the control system is called small time locally controllable from x naught if for all neighborhoods v of x naught and all t r of x naught contains a non-empty neighborhood of x naught. So basically it contains neighborhood of x naught. It contains all v. It is contained within v. In this case, an open set omega is it needs to be. So there is a difference. Some of the trajectories can go up, but here in this case, this is not possible. So let's discuss with an example. Consider the control system in two dimensions. For any initial conditions, the first state component x1 may only increase. So it's going to be increased. We cannot design any control input to contain it. But the second can move in any direction. So we can move it in any direction. Note that the system has two states and single output. Hence, this set of states, okay, with starting from x naught with time t with the neighborhood of v, contains a non-empty open set sigma, but does not contain any neighborhood of x naught, x0 and x02. This is not possible because one of the state is reaching out. Because x2 can be steered, however x1 not. So I said omega of x2 is there. Therefore, it is locally accessible but not small time locally controllable or controllable at all. So an interesting point is the previous definitions, accessibility and small time local controllability, are local in nature. They may be globalized by saying the system is locally accessible or small time locally controllable if it is such for x naught in whole dimensional space. Again, another point, small time local controllability implies local accessibility as well as controllability, while the local accessibility does not imply controllability in general. So it means if system is small time locally controllable, it is accessible as well as controllable. But if it is locally accessible, it does not mean it's controllable. It's kind of the same concept, observable and controllable. However, if no drift vector is present, then local accessibility implies controllability. So if there is a system is driftless, local accessibility means controllability as well. Now back to Siciliano book. Let me zoom in. This is the book we are following. This is chapter number 11. Continued kinematic model. So if 11.11 does not hold system 11.10 is not controllable. So let me go back to my slides and show 11.11 here. This is dimension of accessibility distribution. This is equal to n. If this equation does not hold, then the system 11.10 is not controllable, and kinematic constraints 11.3 are at least partially integrable. In particular, let's say that dimensions of accessibility distribution is equal to v, which is less than n. Then if m, we have discussed it, is less than v and it is less than n, constraints 11.3 are only partially integrable. And if v is equal to m, constraints are completely integrable and hence holonomic. System is holonomic. This happens when delta A coincides with delta, this is distribution, span G1 to Gm, when the later distribution is involutive. So later distribution is involutive, so the system becomes completely holonomic. Now, it is easy to verify that in case of single kinematic constraints 11.7, the integrability condition given by 11.9 is equal to the involutive of delta equal to span, which is equal to space which spans G1 down to Gn minus 1. So let me go to the 11.7 and 11.9 to describe it. So here this is 11.7, this is the Pfeffin constraints, and this is 11.9 is Schwarz theorem. Um, so uh, Kinematic constraint 11.7 is basically E transpose Q into Q dot equals to 0. The integrability condition given by Schwarz theorem is equivalent to the involatility of this accessibility distribution which span the space. There is one more interesting situation when the number of Pfeffin constraints is k, which is n minus 1. So just one less than the actual configuration space. In this case, the associated kinematic model 11.10 consists of a single vector field, that is m equals to 1. So there's going to be only one vector field and m is going with one input. Hence, n minus 1 Pfeffin constraints are always integrable because the distribution associated with a single vector field is definitely always evolutive. For example, a mechanical system with two generalized coordinates that is subject to scalar Pfeffin constraint is always holonomic. Let's go further. So there is this is a unicycle mobile robot model. The configuration vector is Q, it contains x, y, and theta. The pure rolling constraints for the disk is expressed in the Pfeffin form as x dot sine theta minus y dot cos theta is going to be equal to this one, sine theta, cos theta, and yeah, definitely. So it's going to be in the form of x dot, y dot, and theta dot, which is theta dot, that is going to be multiplied with this, it's going to be equal to 0. And entails that in absence of slipping, the velocity of the contact point has 0 component in the direction of orthogonal to the sagittal plane. So it means that, and this is my x direction, this is my y direction, this is my theta. It cannot go sideways. It's going to be either can go forward or backward, or can rotate. Okay, so it cannot move in the direction of y directly, obviously. Now consider this matrix with the vector field G1 and G2. I have already explained that the kinematic model of unicycle is written in this form, where V is represent driving velocity and steering velocity, so V and omega. So let me say that now I'm going to start a scary robotics. It's going to be really problematic, and I'm sorry I have to go through this to make my point. So I'm gonna, for some point, I'm gonna follow this book by Stephen M. Lavelle. Please excuse my pronunciation. I'm going through this because I want to explain every single concept. If I'd missed that, it would be very difficult to grab it. Okay. First of all, topological space. Basically, topological space is a pair S and O, where S is a set and any set, and O, sorry. Um, so topological space is a pair S and O, where S is a set, any set, and O is as a collection of subsets, which is as a whole is a subset of 2 raised to power S. There. So if you make, say, so it's going to be O, which is going to be the subset collection of subsets. So all the collections possible for a set S, and it's called open sets satisfying following axioms. Number one, null set is a part of this O, and S is itself is a part of, sorry, S is okay, it's a part of O. It's not equal to phi, so it's equal to O. So number one, there is a set and it has members, and if you take all the members and make it all possible subsets, and, and name it O, then this collection of subsets, which are called open set, if they satisfy following axioms, then that pair is basically topological space. So another thing is that a union of any number of open sets is an open set. So you combine all of these open sets, and then still you get open set. So if O1 and O2 that belongs to O, and then intersection of O1 and O2 is going to be equal to, is also going to be equal to in O. The intersection is in O, their itself is in O, so that's what is topological space. Given a set S, a collection of subsets O for which S is a topological space is a topology on S. Okay, so why it is important is very interesting to note that in a broader spectrum, basically the basic space is you can define all spaces in topological spaces. And under topological spaces, there comes metric spaces, and then norm spaces, and then inner product spaces. In mathematics, a metric space is a set for which distance between all the members of sets are defined. So that becomes metric space. And norm space, a vector space is over the real or complex numbers on which norm is defined. So in a metric space, the distance, and in this norm is defined. So in inner product, in linear algebra, inner product space is a vector space with an additional structure called an inner product. So it's going to be the inner product. So if you see as a whole, this we can define all of these spaces in topological spaces. So let me do it one more time. And I have taken this definition from this book. Okay. So a topological space is a pair SO where S is a set and O is a collection of subsets called open sets. So this collection of subsets satisfying the following axioms. Number one, this empty set belongs to the open set O, and S itself belongs to O. A union of any number of open sets is still an open set, and any sets O1 and O2, which are the members of this open set O, their intersection is going to be also equal to the member of this. So if a given set S, a collection of subsets O for which this is a topological space, is called S, it's a topology. It's called a topology on S. Okay. And then I want to describe first countable. Let S, O be a topological space, then S, O is first countable if for every x that belongs to x, there exists a sequence of neighborhoods j from j belongs to n u of j of x, such that for any neighborhood u of x, there exists j which belongs to natural number with u of j is a subset of u. So what I'm trying to describe is that a sequence of neighborhoods exist, okay, for any neighborhood u of x, and this sequence can be is countable, and this belongs to n natural number, and this uj is going to be the subset of this u. So that becomes first countable. It simply means that the trajectory is continuous to in a rough way. Okay. Now the basis, a subset B that is subset of O is a basis for O if for every O that belongs to O there exists an index set A and a collection of sets B of definitely A, and A is a member of definitely capital A, and this is going to be subset of this stylish B, such that O that is equal to union of all the A's be A. Okay, so basis. So this becomes basis for O. Also, it is said to be B generates O. So B is a set which generates O. Basis vector basis generates the set. Okay. Let me try it one more time. So basically, it is saying that for every O that belongs to this O, an index set which is exists, and a collection of sets which is like B, and for B1, B2, where A belongs to the capital this A, index set A, it's going to be subset of B. So you can pretty much define this O, which is a member of this O stylish, and such that if you combine this all these BAs, okay, union, that becomes O. So there exists some basis. Okay. So also it is said that B generates O. That's B is generating O. So if you can generate the whole this O by using this space, this becomes this basis. It's just like for metric space, it's like if you're moving in 3 dimensions, if you have matrix, it's going to be x, y, and z, and those 3 vectors in space are linearly independent, and you can span the whole space by using those basis vectors. So if S comma O is second countable if it has countable bases. So if the bases are countable, then it's second countable. Here I would like you to please watch this video. It's interesting.
Hello and welcome to this video on manifolds. Let's start with the temperature of the surface of the Earth, which is simply a map T to the real numbers R. We'd surely want this map to be smooth. But what could smoothness mean in this case? In fact, what could it mean for any map from some kind of object to another? In mathematics, maps and spaces are bound together tightly. For example, a linear map preserves the linear structure of a vector space, or a group homomorphism preserves the group structure. What could this mean in our case? Which kind of structure do the Earth or other objects need for smooth maps to be defined in between them? First of all, remember that differentiation involves taking limits, and every smooth map is certainly continuous. For these concepts to make sense, we need a notion of open sets in our space. This is provided for by calling our space topological. Furthermore, these limits ought to be unique. And so we require any 2 points of our space to be separated by 2 non-interfering open sets. This property is called Hausdorff. With this at hand, we can go back to the temperature of the Earth and find out which kind of structure smoothness requires. Now here comes the crucial observation. If we zoom in and look at the temperature locally, we find an ordinary map from some subset of R squared, which is given by the gray axis, onto the real numbers given by the red axis. But for this kind of map, we surely know what smoothness means. So how can we express the zoom procedure mathematically? Here is how. Our local set, let's call it U1, is homeomorphic to its subset V1 in R squared. That is, there exists a continuous map phi1 from U1 to V1 with a continuous inverse. This map is called a coordinate function. So what we actually considered when we zoomed in was the composite map T of the phi1 inverse, for which we surely know what smoothness means. Going back, we just zoomed in here, but we can also zoom in here, or anywhere, and find a map from R squared to R. In the end, we have covered the whole surface with sets and got an atlas of the Earth. Of course, there may be two or more charts covering the same area of the Earth. In this case, we require the transition maps or coordinate transformations phi beta after phi alpha inverse to be smooth. Now we are ready to give the full definition. A topological space M is called a d-dimensional smooth manifold if it is Hausdorff, it is second countable, it comes with a family U alpha phi alpha with open sets U alpha and homeomorphisms phi alpha such that M is the union of all U alpha and the transition maps are smooth. The pairs U alpha phi alpha are called charts, the whole family atlas, and the phi's coordinate functions. You might have noticed that we required our space to be second countable. This makes every connected component of our space in a certain sense compact and ensures that integration will be well defined. So what about our map F between these two-dimensional manifolds? We want it to be smooth, no matter which kind of local coordinates we choose. So we say it is smooth if psi beta after F after phi alpha inverse is smooth for all alpha and beta. If you'd like to dig a little bit deeper into this topic, take a look at the books by Spivak, Nakahara, or any other differential geometry or topology book. If you'd like to see more videos on certain topics here on YouTube, hit the like button, comment and share this video with your friends.
Okay, this was a really nice video explaining manifold and stuff like that, and I that's why I included it in my lecture. I hope you might have got it. So I have already described leap derivative, and back to unicycle robot. So accessibility distribution for unicycle robot is going to be this G1, G2, and the leap bracket. The dimension of accessibility distribution is equal to 3, and all of the vectors in the accessibility distribution are linearly independent. So it is understandable that these vectors span the space, as in total it has gone up to 2 degrees, like C, B, and AB. So it's going to be B and it's going to be AB, where G1, G2 represents leap bracket. Therefore, the degree of non-holonomy is 2. Again, it is interesting to highlight that in the same way, bicycle model has degree of holonomy 3 because it takes B, A, B, and A square B. It is important to mention that B here is equal to G1 and G2. I would also like to discuss bicycle robot model. So a possible choice for the generalized coordinates is x, y, theta, and phi. Phi is definitely the front wheel angle. Theta is general orientation. So Cartesian coordinates, these are the Cartesian, x, y are the Cartesian coordinates of the contact point between the rear wheel and the ground. That is of the rear wheel center. And theta is the orientation of vehicle with respect to x-axis, and phi is the steering angle of the front wheel with respect to the vehicle. So it's going to be like that. The motion of the vehicle is subject to two pure rolling constraints, one for each wheel. So front wheel x dot f sine theta plus phi minus y dot f cos theta plus phi is going to be equal to 0. And the second constraint x dot sine theta minus y dot cos theta is going to be equal to 0, where x, f, and y, f is the Cartesian position of the center of the front wheel. Using the rigid body constraints, x, f is equal to x plus l cos theta and y, f is equal to y plus l sin theta. It's because this is x plus L cos theta and y plus L sin theta. So we are going to use this length and this structure, where the distance between the wheels constraints 11.15 can be written as x dot sin theta plus phi minus y dot k cos theta plus phi minus L theta dot cos phi equals to 0. This is going to be the distance 11.15. This one, this constraints. We're writing this, rewriting this. Matrix associated with affine constraints 11.16 and 11.77 is then this one. So sin theta plus phi, cos theta plus phi, 0 minus L cos theta, 0 and 0. So the dimension of null space is n minus k, which is 4 minus 2 inputs, 2 equals to 2. And all the admissible velocities at Q may be written as linear combination of bases of this null space. For example, U1 and U2. So since the front wheel is orientable, it is immediate to set U2 equals to omega. So this one is where omega is the steering velocity, which is phi dot. The expression of U depends instead on how the vehicle is driven. So if the bicycle has front wheel drive, one has directly U1 equals to V, where V is the driving velocity of the front wheel. The corresponding kinematic model can be written as this. And here G3, obviously G1 is equal to this one, G2 is this one, G3, G1, G2 is this one, and G4 is this one. And it want to be noted is that both linearly independent from G1 and G2. Both of these vectors are independent from this G1 and G2. Hence, the iterative procedure for building the accessibility distribution, this is delta subscript A, ends with this is equal to 3 and this is going to be equal to 4. This means, I'm sorry, I don't know what happens. Okay. So it's span 4. This means that the front wheel drive basically is controllable with degree of non-holonomic k equals to 3, because G1, G2 is going to be equal to 1, then G3 and G4. So it's basically 3 and basically we have taken b raised to power a raised to power 3. So that's why the degree of non-holonomic is 3, and the constraints 11.15, 16 are completely non-holonomic. Thank you very much. In my next lecture, I would continue with chain form. So I hope you might have enjoyed it. If you have any confusion, I know there would be many. So please let me know and I would love to explain it.